right, in comp 2, it's a bunch of questions on buffers. Buffers are a combination of an acid and base together. So you should never have like 2 acids or 2 bases. You should have 1 acid and 1 base in there. And together they resist the change in pH if an additional acid or base is added to the mixture. So traditionally, buffers that we recognize are going to be weak acids and its conjugate base, and this is usually coming from a salt. It could be a weak base and its conjugate acid, again coming from a salt. But you can have buffers with strong things. We can have a strong acid and a weak base make a buffer, but we need less moles of this, right? And then we could also have a strong base and a weak acid, but again, sorry, this should have been a strong base. We can also have a strong acid and a weak base. Because again, it should be acid base, as long as the strong thing has less moles, molarity. Because if the strong thing and the weak thing are equal, this is just going to win out, and it won't be a really good buffer. So whenever you need to find like the pH of a buffer and you recognize it's a buffer, you can do ice tables, and we've been doing them, but I love this formula because it makes things go a little bit quicker. You saw it on the last video, and so if you see me use this, I'm only going to use this when I recognize that it's a buffer. All right, so once you have this mixture of acid and base together and we know we have a buffer, if we were to add something additional to it, we would resist the change in pH. The buffer would resist the change in pH by attacking the addition. So for example, let's say I have a buffer and it's made of the weak acid HF and the salt NaF, right? So this is a buffer because this is a weak acid. This salt we would ignore, and right there is a weak base. And so my buffer is HF and F ions. So let's say I add a base, like some random base to this buffer system. Well, bases produce hydroxide. So you have to ask yourself, well, which one of these can neutralize that so our pH doesn't change? And it's always the opposite. If I add a base, my acid's gonna come in and take it out. And so remember, acids give away a hydrogen. And so you can see on the other side, our hydroxide is gone. So now that can't raise the pH anymore. We have F and we have water, and that's a lot better to have than hydroxide. This makes our pH increase. This would have to go on and react with water and like make a way smaller amount of hydroxide. Let's say I have this buffer again, but this time I add an acid. So acids are going to create hydronium. So out of these two things, the base is going to attack it. And bases accept hydrogens. So instead of having hydronium, we're neutralizing it, we're taking it out, and look, we're making water. And so we won't be able to bring the pH down as much. And so I answered this question right here and this question right here. And so you might have to make these types of reactions. And so just so you see another example, let's do this one. We have HCN with KCN. All right, weak acid, basic salt. If I add an acid to it, then my base takes it out. It's going to make H2O and HCN, and so now my pH can't change because that's gone. If I add a base to the buffer, then my acid's going to come and take it out, and it's going to give a hydrogen away and make water and CN. And so now my pH can't go up because I'm taking that out. I'm creating these two instead. All right, so the first question I'm gonna do is actually going to be this top one, and then I'll go back to the others. What's the pH of a buffer made by dissolving this many moles of this weak acid and this many moles of this salt in a 1 liter solution? So instead of an ice table, I'm going to do hydrogen equals Ka times the acid molarity. The acid is the 0.35 over the base molarity, 1.1. And once I get that hydrogen concentration, I'm going to take the negative log of it. So I'm going to pause it real quick, get this answer, plug it in here, and get my pH. So I got 0.0035. Take the negative log of that. I'm getting 2.46 as the pH of this buffer. All right. In the problem right underneath that, we'll just go ahead here next. We have a solution at 298 kelvins, and how did we make it? We dissolved this. This is a salt, and just while we're here, this is an acidic salt, right? We would ignore Cl, and there's a there's the Ka of that weak acid right there. After it's at equilibrium, 2.5 moles of NH3 is added to make a buffer. Because look, that's a weak base, and they're conjugates of each other, all right? Weak acid, but it's a weak base. It's a weak base. Assume the change in volume is 0, because that way we can assume our molarities don't change. And what is delta G before we can reestablish equilibrium? So anytime we don't have a chance to reestablish equilibrium, we have to pull out this formula from our last unit, right? We know R, we know T, we know K. There it is. We know R, we know T, and let's find Q. All right, so once we find Q, we can solve for this. So we are going to set up an ice table. We have that NH4, and it reacts with water, and it's going to produce NH3 and hydronium. And the reason we're doing this is because Q would be NH3 times hydronium over, we don't care about water, NH4. So we're going to find these values at equilibrium and plug them in, but then we're also going to add this to our NH3 and figure out how it messed it up. And I can see right away, if I'm adding NH3, should shift this way. So when we're done, we're hoping for a positive delta G, all right? So at the beginning, since this was a salt, salts would ionize completely. This should be 0.35. So we're going to shift the opposite way. All right, and we would say 5.56 times 10 to the negative 10th, that's our K, equals x squared over 0.35 minus x. And we're going to ignore that for the quadratic formula. So let's go ahead and solve for x. Okay, so I'm getting 1.39 times 10 to the negative 5th for x. So I'm going to come over here to Q, and I'm going to plug that in for NH3, so that's what it was at equilibrium, plus those moles that we added over 1 liter would still, we can just add it. And then H3O, 1.39 times 10 to the negative 5th, over, and since we ignored that x on the bottom, we can ignore it. We can just plug in 0.35. All right, and so Q equals 9.96 times 10 to the negative 5th. I already told you we should shift to reactants when we add this, and that's what we're seeing here. And so finally, we're going to plug in everything we know. Negative 8.314 times our 298 temperature times the natural log of K, 5.56 times 10 to the negative 10th, plus R, 8.314 times our temperature, 298 times the natural log of Q, 9.96 times 10 to the negative 5th. All right, and then finally, we'll get our delta G. And so we're getting a positive G, which again supports the idea that we're going to shift backwards after adding our NH3. All right, and so the last question we're going to look at in Comp 2, because a lot of them are just like, hey, what are the following could be buffers, is this one right here. So we have 10 milliliters of a 1 molar HBr solution, and so that's a strong acid. It's reacting with 20 milliliters of a 0.1 NH3, and so that's a weak base. And so The only way this would be a buffer, which it seems like it probably is that if we have less moles of this. So to find moles, you can do molarity times liters. But at the end, it wants to know what's the molarity of everything after the reaction. Okay, so the molarity of everything after the reaction would be, hey, let's figure out HBr at the end, NH3 at the end, NH4 at the end, and bromine. And so on a test, I don't think you would have to find all of these, but you might ask for like one or two. So molarity for all of these will be over total volume, right? After the reaction, how many moles do we have over total volume? So I'm just going to go in and plug in total volume now. 30 milliliters. So the denominator for each one, I'm going to go ahead and make 0.03. And so that just means now I need to figure out moles of all these things at the end. So let's figure out moles that I start with. So I'm going to pull out our old Stoich chart. I'm plugging moles of what I start with, find my limiting, work them over, and see how much I have at the end. And then we'll go from there. So above each one of these, moles is molarity times liters. I did molarity times liters. That's how I got that. Moles is molarity times liters. I did that right there. That's how I got that. We have our balanced equation. And so do y'all see at the very end of this reaction, there's not going to be any acid left over. So that's why this is a buffer. We have less of this. So we can't overtake or neutralize every single NH3. So at the end of this, we could say there will be no HBr left, right? You can put in 0, but that's your limiting reagent. That means you run out of it. So let's move that guy over here. And so now I can see at the very end of this, I'll have that many moles of NH4. Let's move that over here. At the very end of this, I know I'll have that many moles of Br, right? And so now, how much NH3 do I have left over? So we subtract our two equivalents and we work up the excess column. And when I do that, I get this. Now this is why it's a good buffer, because at the very end of this, I go get the molarities for each of these things. They ended up being the same. Do y'all see how I have a weak base and its conjugate acid, and they are equal molarities? So together, these two are really where the buffer's coming from. It took this to create it, right? But we don't have it left over to mess with us. So that's why this thing is a good buffer. And this is negligibly weak. So yeah, it's in the buffer solution, but it's not really doing anything. And so there's the molarity of everything after the reaction.